Welcome back, everybody. Shout out to all the people watching along at home. So section now the chapter 7 test again. I'm in the process of grading. I gave a test all day on last Thursday, so it's going to take me a minute to grade them. Especially because this was a full 4-page test. It's going to take me a while to get those graded in the grade book. I'm hoping by the middle of the week, but we'll see. I got a full night tonight. My washer bit the dust last night. Got water all over the bit, like the clothes washer, but it stopped like mid-cycle. So there's water in the thing, and then it just started leaking out the bottom. So there's water all over the base. So luckily there's a drain right there. It's not finished in that part, so I gotta go buy a new washer and dryer tonight. That's fun. Woohoo! That's what I wanted to do. Right, forever, for the rest of my life, just be like, get a washboard out, right? Old timey. But so I don't know if I'm going to be able to get any grading done tonight. I'm going to try to as much as possible. I'm going to try to grade throughout the day. My goal is to do a quick set of notes and let you guys work on your homework in class. Does that sound good to you guys?
Yep.
Yeah. I know Mrs. Napples and Mr. D-Lab, they might be going over their tests in class, but we can't do that because we're not graded yet. So let's get started here. Section 8.1. Now, I'm going to hand out the guided notes here. Now, chapter 8. Okay, chapter 8. You know how in chapter 7 we learned how to multiply? Yeah. In chapter 8, thank you, John. In chapter 8, we learned how to kind of unmultiply. We learned how to not necessarily divide, but we learned to what's called factor. Okay? We're going to spend a whole chapter talking about factoring. Okay? A whole chapter talking about factoring. And again, like I said at the beginning of this new semester, chapters 7 and 8 and 9 are very important in terms of the scope of Algebra 1. They're big topics within Algebra 1. Like, I can't let you leave this classroom if you don't know how to factor. And I can't let you leave Algebra 1 if you don't know how to factor. You have to know how to factor. We're going to spend a long time, pretty much, and I got to be honest, this takes us through a majority of the third 9 weeks, okay, learning how to factor. Okay? Factors and greatest common factors. All right, so let's start here by talking about the whole numbers that are multiplied to find a product. They're called factors of that product. For example, if I want to think about the factorizations of 12, and you see them on your guided notes there, if I want to talk about the factorizations of 12, I figure out the things that I could do to multiply to get 12, like 1 times 12, 2 times 6, 3 times 4, 1 times 4 times 3, 2 times 2 times 3. Those are all factors of 12. 2 is a factor of 12. 3 is a factor of 12. 6 is a factor of 12. Any factor is one that I could divide that number by, and it would come out as a nice even thing. Like, if I wanted to say, like a factor of 50. Is 5 a factor of 50? Why?
5 times 10 is 50, for example.
Right. If I divide 50 by 5, I get a nice even round 10. Right? I get a nice whole number. Okay, so what do we call these are what's called the factorizations of that number. The factorizations are, okay, what are the products? Like 5 times 10 is 50. Okay, 5 times 10 is 50. Now, each of these are good, but this one is pretty unique. This one on the end here is pretty unique. Why is that one unique? Can anybody tell me? It's got to do with what type of numbers 2, 2, and 3 are. They are all prime numbers. So 2 times 2 times 3 is what's called the prime factorization. The prime factorization. The order of the factors does not change the product, but there's only one of those examples that cannot be factored down further. The circled factorization is what's called the prime factorization. We're going to spend a while talking about how to find what's called the prime factorization. The prime factorization is when it cannot be reduced, cannot be expanded out anymore. Like for example, why is 2 times 6 not a prime factorization? Well, because 6 is not prime. Can't I expand 6? Can't that be 2 times 3? So the full prime factorization is 2 times 2 times 3. Can't I break down 3 times 4? Yeah. Isn't 4 2 times 2? So this is 3 times 2 times 2, which is essentially the same thing as 2 times 2 times 3. Can't I break this down more? Yeah. Now, what's going on with this 1 that's sitting out there on the outside? Well, people, 1 could be multiplied to anything, right? Can't I put a 1 in front of everything if I really wanted to? 1 times anything, and then multiply another 1, and then multiply another 1 if I really wanted to. So we're going to kind of just leave that 1 out of our prime factorization. The prime numbers have exactly 2 factors. It's actually technically not prime because by definition, a prime number has only factors of 1 in itself. Well, prime factors have just 1, so it's not necessarily a prime number anymore. Okay? All right. So let's find the prime factorization. Let's write the prime factorization of 98. You know what the best way to do this is? A good old factor tree. Have you guys done factor trees? Let's do it. Let's a long time ago. Galaxy far, far away. Let's do a factor tree. What does that mean? Well, I find a number that can reduce 98. It can divide 98. Somebody find one for me. What number can divide 98 evenly? 2. It's even, right? Can't I divide 98 by 2? Somebody tell me what I get when I divide 98 by 2. 49. 2 times 49. Could I have picked any factor there? Well, yeah, as long as it comes out to be a whole number. All right. I then keep checking to see if those numbers on the bottom are prime. Is 2 prime? Yes. Because the only thing I could break it down with is 1 times 2. So therefore, it is a prime number. So I leave it like that. Some people would say to circle those numbers that once they're eventually prime. And then I take a look at 49. What numbers is 49 prime? No. What can I break not 49 as? 7 times 7. Very good. 7 times 7. That's a perfect square, right? 7 times 7. Now, I then keep checking. Is 7 prime? Can I divide 7 by any number other than 1? No. So 7 is prime. That must mean this 7 is prime. Okay, I see 2, a 7, and a 7. That means the prime factorization is 2 times 7 times 7. Times 7. I almost wrote another 2 in there. 2 times 7 times 7. That's the prime factorization of 98. Questions about that? Okay, let's do one more, and then you're going to do one. Let's do the prime factorization of 40. All right. Now, I can pick anything I want. So what do you want to break down 40 with? 10. Okay. So 10 times 4. Is 10 prime? No. What can I break 10 into? 2 times 5 or 5 times 2. It doesn't really matter the order. 2 times 5. Okay. Is 2 prime? Is 5 prime? Okay, then I come over here. Is 4 prime? No, it's 2 times 2. And those are both prime. All right, so my prime factorization, I like to go in order. I've got 3 2's and then a 5. Is there another way I could write that? Okay.
You do 2 and 20 instead of 10 and 4.
Right, I could have done 2 and 20 instead of 10 and 4. I could have done 8 and 5 instead of 10 and 4. Now, let's take a look at the actual prime factorization. This 2 times 2 times 2 times 5. Is there another way to write 2 times 2 times 2? Tyler? Yeah, very good. It's 2 to the third. If you wanted to, I could have written this, 2 to the third times 5. Those are both equivalent statements. I don't mind if you write it out. I really don't care. But we know 2 times 2 times 2 is 2 to the third power. Okay, do 33. Do that last one. Don't say it's prime. It's not prime. It's kind of an easy one. What's the only thing that divides 33? Well?
11.
And 3 times 11. Is 3 prime? Yep. Is 11 prime? Yeah. So this is just 3 times 11. That's the prime factorization. All right, good. So now we know how to identify factors, right? Now we know how to identify factors. Well, factors that are shared by 2 or more whole numbers are called common factors. It's going to be very important that we talk about, that we know how to identify when 2 factors are common. So let's take a look here. The greatest of those factors is called the greatest common factor. We're going to be looking for the biggest one. It's always important to find the biggest one. The term GCF is used when we want to find the greatest common factor. GCF, greatest common factor. So let's take a look at 2 lists here. Let's find the factors of 12. Well, the factors of 12 were really easy to identify, right? We talked about them on the first slide here. The factors of 12 are 1 and 12, 2 and 6, 3 and 4. Some people said, I've heard people say like, oh, you got to do your factor rainbow. You guys know what I'm talking about when I say factor rainbow? Maybe you guys had teachers like that? Like, factor rainbow. Factor rainbow. Like, how do they connect 1 times 12, 2 times 6, 3 times 4? Everybody needs another side there. Let's think about the factors of 32. All right, factors of 32. Well, that would be 1 times 32, 2 times 16, 4 times 8. And nothing else. Now, what's the greatest common factor out of those? What's the greatest common factor out of both of those lists? Got it? 4. Yeah, the greatest common factor out of both of those lists is 4. So we'd say the GCF is 4. That's what we would say there. So the GCF, therefore, is 4. There is another way to do this. Think about the factors of 12. Well, if I wanted to find the prime factorization of 12, 2 and 6, 2 and 3, so 12 is 2 times 2 times 3. We saw that from the first slide. I'm going to do a quick factor tree for 32 as well. Ooh, look, I'll just use that one. 32, that's 2 and 16, 2 and 8. Oops, got my second bump on the 8. 2 and 4, 2 and 2. So 32 is 1, 2, 3, 4, 5 twos. 1, 2, 3, 4, 5 twos. Let me ask you this. What do they have in common? They got 2 sets of 2s, right? So let's take a look. What do they have in common? Well, then the GCF is going to have those common pieces. A 2 and a 2. Anything else in common? No. What's 2 times 2? And that's the GCF. Okay?
I like the factor rainbow better.
You like the see? Now I can't diss on the factor rainbow. Factor rainbow is a good tool there. All right, let's try another one. I like to use the factor tree, but trees, rainbows, I don't really care. Heart, stars, rainbows, clovers, and balloons. What is that? You guys don't? Lucky charm.
Really?
Heart, stars, rainbows, clovers, and balloons. What is that? Forget the rest of the marshmallows in there. All right, let's find the GCF of these 2 numbers. 160. Now, by the end of this chapter, you guys might be able to say like, oh, I know the GCFs pretty quickly. Now, big numbers like that with 160, Here's what I'm going to do. I'm going to do my factor tree method. Okay? I'm going to do if you want to do the factor rainbow thing, go for it, more power to you. But I'm going to do the factor tree. Okay, 100, let's do 10 times 10. Why not? And then 10 and 10 break down to 2 and 5 each. So that means 100 is 2 times 2 times 5 times 5. And then we said, okay, 2 times 30, 2 times 15, 3 times 5. Okay, so my 60 is 2 times 2 times 3 times 5. All right, so that must mean that my GCF is 2, 2, 5. You see the 2's here, 2's, and then a set of 5's. So what's my full GCF? What is 2 times 2 times 5? What is 2 times 2 times 5? 20. My GCF is 20. Now, you may have been able to come up with that. You might have been able to look at 160 and say, oh, my GCF is 20. They're both divisible by 20. That's a pretty big number. Yeah. Let's do that one more time. Now, you may be able to just intuitively know what the GCF of 12 and 16 are. I would like to get us to that point where we just know what the GCFs are. But if you need to, you can always fall back on your factor tree or your factor rainbow, whatever you like to use. I'm going to start making my trees. You guys get 4? You know what's funny? My wife, who teaches 6th grade math, she teaches this. She teaches this method where you break it down with its prime factorization and find the common parts. You know what else you know what else she teaches in this lesson? Least common multiple. Because least common multiple also deals with the prime factors as well. You basically take all the prime factors and you just make them represent ones. Like, you don't double up the shared ones. You would just say, okay, I've got a 2, and then 2, 2, and 3. And you multiply all of those prime factors out, and that's your least common multiple. Just 10 minutes tidbit. We can also find the GCF of monomials. Ooh, so now we're tying in chapter 7 here. We can also find the GCF of monomials that include variables. This is an important piece right here. To find the GCF of monomials with prime factorization of each coefficient. Write all powers of the variables as products, then find the product of the common factors. Let me show you this. Let's do an example here. Let's find the prime factorization of 15x to the third and 9x squared. So the first thing that I'm going to do is find the prime factorization between the numbers. Now, does anybody intuitively know what the what the GCF of 15 and 9 are? What would you say? 3. Yeah, I would agree with that. 3. Let's double check that. Let's see. Okay, prime factorization of 15, that's 3 times 5, and that's it. And then prime factorization of 9 is 3 times 3. So therefore, I know that 15 is 3 and 5. 9 is 3 and 3. GCF is 3, right? Okay, let's do something else with this. Now let's add in the x's. Okay, well, isn't x to the third written out in expanded form? Isn't it x times x times x? And isn't x squared x times x? So we do that whole piece where we look at what's shared. Yes?
How is the GCF of 3 if they're supposed to meet?
You only look at the common pieces, remember? So you only see, okay, I've got a common piece of 3 there, so my GCF is only a 3. Okay? And now, take a look at the prime factorization of the x's. What do they share? They share 2 sets of x's. So you basically do that exact same process. So now my GCF is a 3x squared. 3x squared. That's my GCF between those two monomials. Now, let's try to create a shortcut. If they share a variable, what ended up being our power in the end? The 2. The smaller of the 2 powers. The smaller degree ended up being the degree of our GCF. Okay? That's a trick that you can kind of bypass all of that work if you would like to. The smaller variable is going to end up being the power on x. Let's try another one of those. As long as they share that variable. Do they share variables here? No. So think about this. Take a look here. 8 is 2 and 4, which is 2 and 2. So 8x to the second is going to look like this. 2 times 2 times 2, x times x. You follow me there? That is 8x squared pulled all the way out, stretched all the way out. 7y to the third. Well, isn't 7 prime? So 7y to the third is going to look like this. 7 times y, that's a y, not an x. Y times y times y. So really, this is going to be, well, do they share anything? They do not. So what's my GCF? When there's no, yes. Well, I kind of do. Because it's tempting to say that there is none. But what can always divide everything? 1. My GCF, can't speak today. My GCF is 1. Because they don't share anything. Try this one on your own. Yeah. All right, here, let's get going. Got 12x and 28x to the third. All right, so 12 is 2 and 6, or 2 and 3. So 12x is going to look like this. 2 times 2 times 3 times x. 28, okay, that's 2 and 14. I like to divide by 2. That's just a habit of mine. And then 2 and 7. So 28x to the third looks like this. 2 times 2 times 7 times x times x times x. All right. So my GCF is going to look like this. Here, here, and then an x. My GCF is 4x. Does that make sense? I want us to be able to get to the point where we can look at 12 and 28 and say, oh, they both divide evenly by 4. And that's the biggest thing that divides them evenly. And then the smallest power. What was the smallest power on the x's? X the first, right? So that's my final power on x. So 4x. Let's do one more here. I've got 27 x to the second, 45 x to the third, y to the second. All right, let's do this one together. I'm going to break down 27. Let's go 3 and 9, which is 3 and 3. So 27x to the second looks like this. 1, 2, 3, x, x. 45. 5 times 9, 3 times 3. So 45x to the third, y to the second looks like this. 3 times 3 times 5 times x times x times x times y times y. All right, now let's take a look at the parts that are shared. I've got a 3, an x, an x. So my GCF is 3 times x, or in other words, 9x squared. Now, I would hope that we might be able to get there without showing all of that work. We're going to need to be able to get there without showing all of that work. Look at the numbers 27 and 45. You should intuitively know that they're both divisible by 9. And that's a pretty big number. Anything other than 9, any bigger than 9? No, that's it, 9. And then you look at, okay, what variables do they share? They share the x. Do they share y? No. So they do, the y is not included in the GCF. And then you just take the smaller power out of the x's. It's x squared. But you can always fall back on this listing on the front side. All right, last problem here. Cafeteria has 18 chocolate milk cartons and 24 regular milk cartons. The cook wants to arrange the cartons with the same number of cartons in each row. Chocolate and regular milk cannot be in the same row. How many rows will there be if the cook puts the greatest possible number of cartons in each row? So we got, a very, type A cafeteria person here. We want them to be we want it to look nice and even. We want to see, okay, equal rows, right? I don't want to have like 8 per row of white milk and then like only 6 per row of chocolate milk, right? I want it to be all the same number per row. So basically what I'm looking at here is I want to find the GCF between those two numbers. That's really what I'm looking for. So I'm looking at 18 and 24. I want us all to try to guess at what you think it's going to be. Before you start doing any factor trees, what do you think the GCF is going to be out of 18 and 24? You know what I always like to do? I always like to look at the smaller number and see what that's divisible by. Because whatever that's divisible by, it's got to match the other number. Like 18. Isn't 18, well, can I divide 24 by 18? Go and check that. 24 divisible by 18? Nah. Well, what else can I divide 18 by? Let's go down our list. 9. Can I divide 24 by 9? No. Bummer. Okay, what's the next one? Can I divide 18 by 8? No. By 7? No. By 6? Yes. I can divide 18 by 6. Can I divide 24 by 6? Yes. 6 is my GCF. My GCF is 6. Okay. My GCF is indeed 6. How can I verify that? 2 times 9, 3 times 3. 2 times 12, 2 times 6, 2 times 3. All right, so my GCF here, I know I'm doing this quick, but we've already gotten our answer. Buddy up, 2 times 3 is 6 is my GCF. Okay, well, if there are 18 chocolate milks, how many rows of chocolate milks are there going to be? 3 rows of chocolate. 3 rows of chocolate. If there are 24 white milks, how many rows are there going to be? 4 rows. 4 rows of white milk with a total of 7 total rows. That's really what it was asking, right? It was asking for how many rows of each, and then what's the total number of rows. Okay, I'm gonna pause the video real quick. So long, everybody at home.